Okay, good morning, everybody. As Silke was already telling you, today I want to talk to you about the Jülich Observatory for Cloud Evolution. That's what JOYCE stands for. JOYCE offers us new possibilities to study the cloudy boundary layer. And I want to show you how we can do this and what we are planning to do in future. All of this, what I will be showing today, is not based on my own efforts alone, but also in close collaboration with Susanne Crevel and our whole working group, which is the AG Inferno, and stands for Integrierte Fernerkundung, so integrated remote sensing in English, but we actually find the name quite cool in German, so we leave it this way. Yeah. Okay. About the contents of my talk today. So, JOYCE is a so-called super site, or an atmospheric observatory. That means we have a multiple number of sensors, passive and active remote sensors, which help us mainly to say something about the processes taking place in the boundary layer. I want to say something general about ground-based remote sensing, the specialities of ground-based remote sensing. Then I want to go a little bit into detail what JOYCE is, what overview possibilities we have, what the objectives of the site are, what projects are running at JOYCE, and what cooperations we have. And the main part of my talk will be about going through the different instruments we have at JOYCE. So telling you how they work, what they can measure, and what processes we can observe with them. If we have time, I will try to go a little bit more into detail into the subject of sensor synergy, which means bringing the different sensors together, using them optimally in a combined measurement mode. Then at the end, I will like to show you just a couple of applications, what we can do with the data we are collecting here, and an outlook, what is planned at JOYCE. Okay, so let's start with the basics about remote sensing. I know you've been hearing a lot about radar, weather radar, polarimetric weather radar. We will now a little bit concentrate not only on radar, but also on passive and active remote sensors in the microwave, but also in the optical region. As you know, most remote sensing methods use electromagnetic waves. And these are used in so-called window regions, where the atmosphere is especially transparent. So we can, from satellite perspective, look down to the Earth's surface or see the clouds. If we are looking in the non-transparent regions, which are described here in blue, the atmosphere is very strongly absorbing due to the different trace gases. We see here the electromagnetic spectrum and the attenuation in dB. The windows, so the very transparent regions, are shown in colored boxes. We have the radio window, where most weather radar and cloud radar, but also microwave radiometers are working in. Then we have the atmospheric window in the thermal part of the infrared spectrum, where we also have very nice possibilities of the remote sensing for clouds and temperature and water vapor. And then we have the visible window, where we can see right through to the Earth's surface or right through to space from the surface. Remote sensing instruments are generally deployed on various platforms, mostly probably most well known on satellites, but also on aircraft, on balloons, and from the surface. So most of the instruments I will be talking about today, have sister instruments or parallel instruments that are measuring from space. So here we see the very famous A-Train constellation of polar orbiting satellites. The A-Train is composed of 1, 2, 3, 4, 5, 6 satellites, which measure different things. They can measure the trace gas concentrations. They are sensitive to aerosol. They measure the components of the water cycle. CloudSat and Calypso are active sensors which can remotely sense clouds by cloud radar and by a LiDAR system. But remote sensing from space is not easy, so 2 of them have already died. CloudSat was close to dying last year, but was saved and is still measuring at the moment. But it's possible to take these instruments down to Earth. Well, this is, of course, not a remote sensing instrument. This is a flying cloud radar, actually. So there's a cloud radar in this box, and it's coming down to Earth. Okay, it's not coming down to Earth from the satellite. It's being transported up on a mountain where we see high potential for the remote sensing of snow. So these cloud radar, which is basically the same instrument as CloudSat has, can also be put on the surface and look upward, as you've already heard on Monday from Pavlos. But we can also position microwave radiometers at the surface of the Earth, similar as are on the satellites such as Aqua, for example. But also, not at the surface, there are also dangers. So it's not only the satellite instruments that can break, but also there are difficulties when operating the instruments at the surface. Here, for example, an avalanche hit one of the microwave radiometers. So this is also very complicated, actually. Things happen which you never reckoned would happen. Okay, so my talk is going to be about ground-based remote sensing of temperature, water vapor, clouds, and precipitation, where I don't want to focus on weather radar because you've been biased strongly towards that in the last couple of days. So it's more about the non-precipitating regime and the processes and the parameters leading to the development of clouds. So why do we need ground-based remote sensing at all? So the question you could ask is, why don't satellites and conventional in situ measurements at the surface give us everything we need? We have satellites covering the Earth. We have satellites measuring clouds and precipitation. Well, if we go to the surface, we can carry out detailed process studies, much more detailed process studies than looking from space, because we have much more direct signals. We are much closer to the clouds, actually, that are interesting for us. We have less disturbances from the surface when we look upward. We can measure with a high temporal resolution at one site, and we can very quickly interchange the configurations of the measurements. Once we have a satellite flying, it's fixed. But at a supersite, we can add instruments or take instruments out, test new instruments. So actually, ground-based remote sensing is also very suited for developing prototypes for future satellite missions. And one important thing, as I already mentioned, are the boundary layer observations. One thing satellites basically cannot do is observe the boundary layer in a sufficient way, because the surface is a major source of error, and the vertical resolution of most satellites is just much, much, much too poor to say something about convection, for example. So this is where really the ground-based remote sensing comes into play. Continuous observations, compared to radio sounds, for example, where we only have typically twice daily sounds at dedicated sites. At a supersite, where we observe the temperature profile and the humidity profile, we can capture the diurnal cycle very nicely. So we can really say something about the mesoscale developments along the course of the day. We cannot capture this with 2 radio sounds a day. So we can see when the boundary layer builds up, when it collapses, when the clouds begin to form. But also, this atmospheric ground-based remote sensing technology is developing very fast. So in the last decade or so, we've made an incredible step forward towards 24/7 operation. Unmanned networks and the instruments are becoming more and more affordable. So there are now emerging networks which are coming into play and which are becoming more and more important for the numerical weather prediction. One international European project who is dealing with such emerging networks is the Cost Action EG Climate. It stands for European Ground-Based Observations of Essential Variables for Climate and Operational Meteorology. And you see it's important, this ground-based remote sensing sector. 16 countries have been participating in this project, 13 national weather services. Don't want to read this whole text here, but you see the words inside. So it's about European networks, ground-based profiling, evaluating climate and numerical weather prediction models with these ground-based observations, and assimilating the information at the end into numerical weather prediction models. So the idea was to really see how one can conceptualize a network of new sensors that could be very valuable for numerical weather prediction, for example. So what instruments do we need to put where to improve the weather forecast, or what instruments do we put where in order to get rid of radio sound stations, for example, that are very cost intensive. At the end of the project, which lasted until the end of last year, there was a final report, but also a very nice instrument tutorial that came up. So all of the instruments I will be introducing you to in this talk are also very nicely explained on the wiki page of this EG Climate project. So it's really a putting together of all essential information of these ground-based sensors. So if you're ever interested in finding out any background information, this is the way you could go at the beginning, because it doesn't only give you an overview of the instrument, but it also gives you links to important references. One example network that is operating successfully from the surface is the European Wind Profiler Network CWindy. We see here over Europe the distributed wind profilers. So wind profilers are radars which allow us to capture the vertical profile of the wind vector. And it's basically the reflection, or the backscatter is based on Bragg backscatter, and we are observing organized turbulent elements at very long wavelengths. There are different types of profilers over Europe, 10 which can capture the full troposphere, 21 which are very sensitive in the boundary layer. And it's been a long way to establishing this network, but at the moment these data of these wind profilers are successfully assimilated, for example at the UK Met Office, DWD or Meteor France, even in the ECMWF model. And recent studies show that they really also improve the quality of the forecasts and numerical weather forecast prediction models. So this is one type of instrument, a network of one type of instrument. Now, these supersites are not as frequent. There are only some which are listed here over Europe, but they contain a large number of remote sensors. So there are remote sensors which can give us information on the vertical or along-site temperature distribution. For example, by means of microwave radiometry, infrared spectroscopy, radioacoustic sounding systems, Raman LiDAR, or water vapor distribution along the line of sight of viewing through LiDAR, again, microwave radiometer, or GPS. Then we have the possibilities of having instruments that give us information on the liquid water content distribution within the atmosphere, the ice water content, and the precipitation. And then we also have instruments at these supersites which give us wind direction and speed through Doppler technologies, for example, using new types of instruments called Doppler LiDAR. There are a couple of supersites throughout the world distributed through the ARM program. It's a US-American led program which stands for Atmospheric Radiation Measurement Program. And these were the first to put up such kind of supersites worldwide, so in different climatic regions of the world. But in the last couple of years, there have been a number of supersites which have been installed over Europe. Jülich is just one of the last sites. A couple of years they've been operating one at the Cabau Observatory, which is the main observatory of the Dutch Weather Service, or in France at Palaiseau in Chilbolton is the English observatory. Lindenberg is the observatory of the German Weather Service. So the question you could ask is, what research needs to be done? So these supersites are not about delivering operational projects. It's about, like I said at the beginning, testing prototype instrument configurations, seeing what type of processes can we capture, what instrument combinations lead to what enhancements of accuracy. But the first point is the instrument development and performance. So companies sell their products or loan their instruments to these supersite operators to see if they can perform on a 24/7 basis. So together with the instrument manufacturers at these supersites, these instruments are developed towards continuous operation. There are many aspects, very simple aspects that have to be solved, which I will come back to within the next couple of slides. The other point is the signal interpretation. So once I have an instrument running, how do I convert the signals I measure into the variables of interest? For this, I need to know how my forward operator works. Forward operator means if I know the atmospheric state, how can I get to my measurement? This is the forward model. But what I have to solve is the inverse problem. So I have to do inverse modeling. I have to go backwards from my measurement to the atmospheric parameters of interest. And this all has to do with finding elegant mathematical solutions, because mostly this forward model is very clear. It's directly calculated, but the inverse model is a problem which is not well posed. So once I have this signal interpretation going, I'm interested in the process studies. So then I can look at different days, then I can look at the, for example, the formation of clouds. I can use these processes to go into model evaluation. If the models are driven by the correct forcings from up and below and from the sides, I can try to see if I can see the same processes in the model as in the measurements. And then on the other side, there's the network suitability. So once I have products derived from these stations, from the instruments, are the single instruments or particular instrument combinations suitable for becoming a network instrument, suitable for going into the assimilation system of a weather service, for example. This is all the type of research which needs to be done and which can be done at these supersites. So let's look a little bit more into detail what JOYCE is about. So here's our logo, going from small clouds to large clouds. Tells us, wants to learn something about the cloud evolution. So our observation platform is jointly operated by the University of Cologne, the research center in Jülich, where we will be going this afternoon, and the SFB TR32, which is a large research initiative from the German Science Foundations, which is called Patterns in Soil Vegetation Atmosphere Systems, Monitoring, Modeling, and Data Assimilation. So it's basically about the role of the surface and in interaction with the atmosphere, finding patterns in the surface that lead to certain patterns in the atmosphere. And cloud observations are an important part of this project. So the idea is to find instruments to continuously monitor winds, temperature, water vapor, clouds, and precipitation over many years with a multitude of instruments. This is our main job and our main work to get this running. So this is the region around Jülich. This is the research center where we will be going. So JOYCE is located at the roof of the Institute for Energy and Climate Research at an altitude of about 100 meters above sea level. And it's surrounded by these, by lots of fields with agriculture. Here's the city of Jülich. Does anybody know what these white areas will be? So those are the pit mines of the coal pit mining. So it's directly located in a very industrial area, actually. Okay, so the scientific goals that we have at JOYCE, well, this picture here from Felix Ahmed from Hamburg basically very nicely shows what we want to observe or what we want to know about. We want to follow this arrow here. So going from water vapor, from surface fluxes, from latent fluxes, from sensible heat fluxes, from the influence of the surface and the plants on these fluxes. When will clouds begin to exist? When will they develop into thicker clouds, and when will they begin to precipitate? So specifically, this is driven by water vapor, but often water vapor fields are very much driven by advection. So the idea is to disentangle water vapor variations over the site due to advection and due to local surface influence. So there are coupled models between the Earth's surface and the atmosphere, which we would like to validate. When is a cloud beginning to exist? When is the cloud coupled to the surface? Or when is the cloud a mere product of the advection going above the surface, coming through the synoptic system? How many times are clouds driven by the surface, and how many times are clouds only existing due to the fact that we have synoptic forcing? So the idea is to better understand the development of boundary layer clouds, including the cloud radiation interaction. So there's a big focus also at JOYCE in capturing the radiation effects of clouds. And then, of course, in a step further, to observe the precipitation formation and eventually improve the parameterization schemes in models. So when do clouds actually begin to precipitate? What factors is this dependent on? Is this dependent on the aerosol loading, on the aerosol optical depth in this region, which is very dominated by industry? So these are the instruments which we have, a long list, which most of them we will be seeing this afternoon. So one of our most important instruments is the cloud radar. You've heard a lot about that from Pavlos already. So we'll just be shortly introducing the instrument. Then the microwave radiometer here, which is the second of our workhorses with 14 channels. It also has an infrared pyrometer giving us information on the cloud-based temperature. We have a scanning Doppler wind LiDAR for wind field information. We We have an AERI system, which is a spectrally highly resolved infrared instrument. We have a total sky emitter to show us the cloudy situation above Jülich. We have ceilometers indicating the cloud base height. We have micro rain radar for precipitation in the vertical column above the site. We have SODAR for also wind in the boundary layer, a Max-Dauer system for aerosol, as well as the CMIL sun photometer for capturing aerosol optical depth. Then a bunch of radiation sensors. And there's also a 120-meter meteorological tower, which we'll also be visiting this afternoon. If you're interested in an overview and also what instruments are measuring and at Jülich, you can follow this link here once you have the presentation. Okay. So let's come to the projects that JOYCE is part of or contributing to. One of the most important projects is the current research initiative HDCP Square, which stands for High Definition Clouds and Precipitation for Climate Prediction. So as most of you probably know, clouds and precipitation processes are the foremost problem of climate simulation nowadays. We have the situation that the doubling of CO2 gives us a forcing of 4 watt per square meter over the last 150 years. But clouds have a very large effect with respect to this number. They cool the Earth system within a range of minus 20 watt per square meter. And if in the modeling system we cannot capture clouds in a correct way, we will never be able to correctly predict the influence of CO2 doubling within a climate model. So capturing clouds and their radiation interaction is a very, very important thing for climate models, and it's the most high priority problem to solve in future. So HDCP Square has the objective to cover a high temporal and spatial resolution model over Germany. So the idea is to, over this HDCP Square region here, have a model running with a very high spatial resolution of about 100 meters in the horizontal up to the troposphere. So these are basically LES scales, large eddy simulation scales. And the idea is to capture the clouds within a region over Germany with a very high spatial and temporal resolution. And then to use these long-term simulations basically to come up with new parameterizations for climate models, which you can then run over the whole globe. But the idea is to get a correct picture of clouds. Of course, it's not completely clear to what extent can I really capture the clouds even with a high resolution model. So in this sense, the idea is to come up with a data integration over Germany for clouds and precipitation. So here the supersites present a key component for assessing this small scale model. So to see how well this small scale model can actually represent clouds over Germany. And once we know this, we can trust the model for developing new climate model parameterization schemes. And there's already been a very detailed prototype experiment within HDCP Square. This April, May, mostly all scientists working on ground-based remote sensing over Germany came to the region in the area of Jülich to the research center and built up 2 other supersites. So one other supersite, which normally measures at Karlsruhe, the KIT cube, was built up in a very close proximity to JOYCE, and also the supersite from Leipzig, from the Tropos Institute, was built up. So we had a triangle of 3 supersites measuring with the goal of not only critically evaluating the model at the scale of the model simulations, but also on gaining subgrid variability information of the microphysical processes. So this, what our typical models cannot resolve, we try to resolve with these high resolution measurements during this prototype experiment, which was actually called HOPE, so H-O-P-E. I've already mentioned then as a further project the Research Center TR32. So this is the second important collaboration for JOYCE next to HGCP Square. I was already telling you about that TR32 monitors the land surface interaction with the atmosphere. So for this, over the area here is Jülich, so over an area covering parts of the northern part of the Eifel and a little bit to the north of Jülich, an area, there are many stations which monitor water vapor fluxes, energy fluxes, CO2 fluxes from the surface. So what these fluxes are determined by, what patterns they show. There are soil moisture networks and the plant structures and the interaction of the plants with these fluxes and with the soil moisture are examined. And of course, the idea in combining this with JOYCE is then to assess the role of clouds and water vapor on surface processes and vice versa. So the question would be, how do clouds, when they appear, actually modify these fluxes at the surface? And again, how are clouds modified by the fluxes in a certain situation? So that would be mainly the introductory part of the talk, to show you what the objectives of JOYCE are, who we are working together with. And the main part now is to introduce you to the different instruments that we have. So the first instrument I would shortly like to say something about is the cloud radar. The science issues of the cloud radar are the morphology of clouds. So what phase does my cloud have that I observe? Where is it located? What's the thickness? What are the overlap conditions of the clouds? And a further question is going to the cloud microphysical properties. So how much water is contained in the cloud? How big are the particles? What number concentration do I have? And so forth. So these are the informations we want to get at using the cloud radar. So the principle of the cloud radar is it sends out pulses of microwave radiation, measures backscattered radiation of these pulses, and the strength of this backscattered radiation gives us information on what type of particle or what water content we are observing. And the time between the emitted and received pulse, as you know, of course, is the information on the distance to the backscatterer. So we get a spatially resolved information concerning the strength of the backscatter. Specifications, so we have a frequency of 35 gigahertz, which corresponds to about 8 millimeters. This means that we are very sensitive to cloud droplets, in contrast to weather radars who use much longer wavelength, around 10 centimeters, who are not sensitive to cloud droplets, but only to larger precipitation droplets. But the drawback is then, using this high frequency, we can only get away about 15 kilometers from the radar. So this is the maximum range. So we cannot go out further than 15 kilometers. But we have a very high range resolution of 30 meters, temporal resolution of 1 to 10 seconds. The radar we have is also a Doppler radar. We have polarimetric capabilities and a full scanning capability. So we can scan in azimuth and elevation to capture three-dimensional cloud structure. The measurements we get from the cloud radar are these backscatter values, the radar reflectivity, and the Doppler velocity, which ideally will tell us something about the droplet fall velocity. But as we are dealing with cloud droplets, we also have to consider, of course, turbulence. So we have the combination of turbulence and fall velocity of the droplets which we observe. The Doppler spectra we can also observe, which gives us information on the turbulence itself. And the linear depolarization ratio is the ratio of the cross to copolar reflectivity. This can give us information on the target type. So this means we are sending out linearly polarized radiation at 35 gigahertz. And we look what comes back in the, not only in the plane, in the same plane we are sending out on, but also in the plane perpendicular. And this gives us the depolarization ratio. And this can tell us something if we are looking at spherical droplets, or if we are dealing, for example, with ice particles, or most important, we can discriminate between hydrometeor and non-hydrometeor reflectivities. Non-hydrometeor reflectivities is the so-called plankton. So this is mostly insects disturbing the signal of the cloud radar. And we can get rid of this insect contribution by looking at the linear depolarization ratio. For special periods, we can collect the Doppler spectra, so the full Doppler spectrum, but this we only do on dedicated measurement days because this will take up about 10 gigabyte a day. If you're interested in background information, please refer to this E.G. Klimet wiki site I've been mentioning at the beginning. So this is where the background information is summarized. Yeah, okay. This is the typical cloud radar measurements of a 24-hour time series here. We see the radar reflectivity factor. We see precipitating systems which we can capture. We have here a vertical time-height cross-section. We see the Doppler velocity. So we have large fall velocities in the regions below the melting layer where the precipitation begins to fall. And we have smaller fall velocities up in the ice clouds. Here we see the spectral width, so the broadness of the Doppler spectrum. Often, if we look at the clouds, we are interested in JOYCE. We are interested in these very weak signals here because the non-precipitating systems are the ones that give us reflectivities down to minus 40 or even lower. And these are the clouds which are beginning to develop, which may develop precipitation, and which we would really like to capture at JOYCE. But these are the ones which are the most difficult to detect. So not all of the clouds are detectable for a cloud radar that we see with our other instruments, for example. So this really shows us already that we need to be looking into the combination with different instruments. There are some products which can be operationally derived from these measurements, for example, the ice water content or the liquid water content with simple empirical relations. These are the products from CloudNet. CloudNet is a retrieval, an atmospheric retrieval distribution for the supersites developed at the University of Reading. If you operate a cloud radar at a supersite, you can have this software installed and it will show you that it will directly derive these atmospheric retrievals. But as you probably have learned in the couple of days before you, or that these retrievals are mainly based on the relationships between the moments of the droplet of the Doppler spectrum and the microphysical quantities. And because we are dealing with relationships between different moments, these retrievals have large errors and are subject to the existence of large particles, yes or no. So these products have to be interpreted with care. Okay, the second instrument I would like to introduce you to is the microwave radiometer. The science issues at stake are the thermodynamic state in clear and cloudy cases. So we want to derive water vapor, temperature, and cloud condensate, and observe the diurnal cycle of these properties. We measure along the microwave spectrum so-called brightness temperatures. We can convert the radiance measurements into brightness temperature space, and then we have brightness temperature measurements in the area somewhere between 10 and 300 Kelvin. So this is a practical way of expressing the radiance measurements in the Kelvin unit. So we have 6 channels along the water vapor absorption line, 1 window channel which is very sensitive to liquid water clouds. And then we have 7 channels along an oxygen absorption complex at 60 gigahertz, which can provide us with vertical temperature information. This is the instrument which we will be seeing this afternoon. And what can we derive? Especially well, the integrated water vapor, so the column amount of water vapor. We can derive the liquid water path, the column amount of cloud condensate, with an accuracy of about 20 grams per square meter. We can try to derive humidity profiles. I'm very careful about this formulation because there's hardly any vertically resolving information for deriving humidity profiles. To a certain extent, you can get at least 2 degrees of freedom, which means that you can differentiate between 2 layers of humidity. So you can say, is it moist in the lower part of the atmosphere and dry in the upper part, or the other way around? But remember, you're very accurate concerning the total amount of integrated water vapor. Just the vertical resolution is not very fine. Temperature profiles are derivable to an accuracy between 0.5 and 1.0 Kelvin with a few degrees of freedom more. And again, for background information on this instrument, I can advise you or propose to look at this EG CliMed wiki here. So let's look into a little bit more detail into the retrieval of this integrated water vapor and the liquid water path. So the integrated water vapor and liquid water path, as I was saying, are both integrated column amounts, or we can try to imagine that 10 kilograms per square meter, for example, correspond to a liquid water column of 1 centimeter. This is the microwave brightness temperature spectrum here. We see the frequency between 10 and 100 gigahertz. And we have the atmospheric windows here. And we see the oxygen absorption complex and the water vapor line. Now, the amplitude of this water vapor line is directly proportional to the integrated water vapor. That means if I have an increase in water vapor in my column, this amplitude is directly proportional to this increase. The problem is when a cloud comes. So let's say a cloud with a liquid water path of 250 grams per square meter comes over the site. What do you think will happen with this brightness temperature spectrum if the cloud is above our site? Any idea? Will it lead to a decrease or an increase of the brightness temperatures, or will it be spectrally dependent? An increase? Okay, so that's true. Where's the increase going to be the highest? The high frequencies, but especially in the window regions. So these are the regions which are not determined by the water vapor or the oxygen absorption, but these window regions are very sensitive to the existence of liquid water clouds. So this is here, we show the frequency. 31 gigahertz is somewhere here. 36 is another typical measurement frequency in this window region. 90 gigahertz is at higher frequencies at the window. So we see here that this cloud leads to an increase of 50 Kelvin, 9, and 12 in this lower region. So typically, very simple microwave radiometers measure at frequencies at the absorption line at 24 gigahertz, but also in the window region at 31 gigahertz. Special radiometers can also measure at 90 gigahertz and at higher frequencies. But typical radiometers in this region here. So as I was saying, the integrated water vapor amount, if we have no clouds, is directly proportional to this TB24. So if we don't have any clouds, we could just have a linear relationship between IWV and TB24. So what happens when a cloud comes? Of course, also there will be a slight enhancement at 24 gigahertz due to the cloud. So in order to capture the water vapor in the column correctly, we need to correct for the cloud part of this signal. So we have to have a coefficient taking the measurement in the cloud sensitive region and subtract this from the water vapor retrieval. So in this case, we will get a water vapor column corrected for the enhancement due to the cloud. And the same is true the other way around for the liquid water path. If we have a pretty direct signal of the cloud at 31 gigahertz, here's the positive sign, there will still be water vapor variability on this cloud signal. So we have to correct for this water vapor variability, which we still see here using the TB24 signal. So if we use these two frequencies and we use a simple multilinear regression, we can basically say something about integrated water vapor and liquid water path very simply. So let's have a look at the typical measurements. Here we have the measurements along the water vapor line. So these are 7. Here's the water vapor absorption maximum. Here's the window at 31 gigahertz. And what we see here is that the water vapor signal, so this enhancement here, is strongest at 22 gigahertz, which is basically the line center. And this enhancement is hardly seen in the atmospheric window. And clouds strongly increase with frequency, but clouds are basically this structure that we see if we have these strong peaks. So we have a water vapor increase over the course of the day, but during this water vapor increase, we also have these cloud signals in the brightness temperatures. And even in the V band, so in the part where the oxygen absorption begins, where the atmosphere is still rather transparent, we see the clouds very strongly. When we go to the region where we have the strong oxygen peak, here we don't see the clouds anymore. This means that our signal is stemming from parts of the atmosphere which are below the cloud. So here we have information upon the lower atmospheric layers. But this would be the retrieval then. So we have here the integrated water vapor amount over the course of the day, where we see this increase at the beginning and the strong increase at the end of the day, and the increase basically doubling the amount of integrated water vapor throughout the day from about 12 to 26, 27 kilograms per square meter. And we can also retrieve the liquid water path, so the total condensate amount within the column. And we see here that these are typical values for boundary layer clouds going up to, in the extreme case, of 1,000 gram per square meter. So notice the difference of the size of the condensate in the column and the size of the water vapor in the column. So we're talking about 1,000 grams here, so 1 kilogram at maximum. So this is only about 10% of the amount of vapor contained in the atmosphere in the extreme case. We can also scan with our instrument. So we can scan the microwave radiometer in elevation, but also in azimuth. So in all of the measurement directions where we measure, we can obtain information along the path integrated water vapor amount, and then map this to the zenith. And when we map this to the zenith, we get hemispheric charts of the integrated water vapor. So we see in what direction we have enhancements of water vapor, and in what directions around Jülich we have lower parts of water vapor. And if we assume some simple things about the water vapor profile, here's the same profile measured during this time from a radiosonde. If we idealize the profile of the water vapor, of the absolute humidity as being constant in the boundary layer and exponentially decaying above the boundary layer, then if we scan the whole azimuth in 360 degrees, we can, with some mathematics, derive the horizontal gradient in the water vapor density. So we can really say in what direction we have an increase of water vapor in the boundary layer and where this increase is the strongest. And then we can use this linear field of an increase in a certain direction to correct for the water vapor, which is the water vapor variation, which is basically due to this gradient. The gradient is mostly due to advecting water vapor from a certain direction. And if we subtract this advection field, then we can make a plot here of the remaining of the residual, which then shows us the water vapor variations due to the turbulent structures. The temperature retrieval is done in a similar way. But we have to look at the spectrum again. So I was saying this is the O2 absorption here around 60 gigahertz. So we have a very opaque atmosphere. So at the top, if we measure at 60 gigahertz, the atmosphere is completely opaque. That means basically we only receive information if we measure here from the lowest layers of the atmosphere. The further down we measure in frequency, going down this line, the more information stems from the higher parts of the atmosphere. And this is where we get the profile information from. And why does the profile information on temperature come from the O2 absorption? Well, because we are assuming a well-mixed atmosphere concerning the oxygen. That means the variations in the absorption are not due to variations in oxygen itself, but the variations that differing temperature leads to differing absorption. So, but can we use any additional information to retrieve the profile of temperature? Can we only use frequency-dependent information? No, we still have the possibility of doing elevation scans with a microwave radiometer. So what I was showing with this spectrum and the view graph before was solely of a zenith-looking microwave radiometer. But the microwave radiometer can also be used to do elevation scans in certain directions. So this will give us additional temperature profile information if we measure at these optically thick frequencies. So we can imagine that we are looking at an elevation angle which is very low. So for example, around 5 degrees. Then we only get information from the lower parts of the atmosphere. So because only the radiation is only being emitted along this path. The higher we move with the elevation angle, the more information stems from layers above. So this elevation information is depending on horizontal homogeneity. So we are assuming then that the atmosphere does not change in the horizontal direction, so that the layers are horizontal homogeneous. But in this case, we can directly try to see what a typical temperature profile with an inversion here in 200 meters will do. So let's have a look here. If we have an elevation of 0 degrees and we go slightly upward, we see our temperature decreasing. This is the small decrease of temperature down here, where the atmosphere is becoming unstable. And then we have an isothermal part. So this may be a profile at the very beginning of the day. And then we have this isothermal part. So if we go higher with the elevation angle, we see this isothermal part. And then we see this increase of the brightness temperature, which shows us this inversion. And then at a certain elevation angle, we get a decrease of the brightness temperature, which shows us this normal decrease of the brightness temperature, of the temperature with height. So from this elevation angle dependent brightness temperature measurement at these optically thick channels, we can say something about the temperature profile in addition to the frequency dependent information we have. So this is the potential temperature retrieval for such a retrieval using the frequency and the elevation angle dependent information. So what we very, very nicely see is the very stable boundary layer in the morning parts or in the night, and then when the sun comes out, the atmosphere becomes to be very well mixed, so we have a very constant potential temperature within the boundary layer. But it also works in clouds, so this is important to note that next to the other instruments, for example, that instruments in the infrared, this works also in cloudy conditions. So this is the big benefit of microwave radiometers. So this is another measurement example. What's happening with our measurements in Jülich. Does anybody have an idea what this could be? This doesn't look like a cloud, does it? Doesn't look like water vapor either. You could say, well, it's some kind of radio frequency interference, but this would have to be very broadband because it's going through all of the 7 channels. It was actually about a party on our instrument. They seem to really love it. These are the very young crows coming at the beginning of the summer. And they like to sit on the instrument and do all sorts of nasty things. For example, pick into our radome, make holes in our radome, leading to the fact that water will enter the instrument, which is not very funny. Yeah, there's one sitting. There's even one on the camera here, right? You see here. And then, you know, after having the party, it's time to rest, and then you just sit on the nice and soft radome. And this is what then makes these large peaks, because these birds, as all of you do too, emit microwave radiation. So this is something we've been coping with for a long time, and is actually very difficult to get rid of. Okay, a second instrument that is interesting that we are looking into at the JOYCE site is a passive system called an infrared spectrometer. It's the so-called AERI. It has the possibilities of also deriving water vapor temperature and cloud condensate, and also to observe the diurnal cycle, but is additionally sensitive to aerosol and trace gases. And cloudy is put in parentheses here because in the infrared we have a very high sensitivity to clouds. That means we cannot measure in cloudy situations only with very thin liquid water clouds, in contrast to the microwave instrument. So we have an automated instrument measuring the downwelling infrared radiation at a very high resolution in the thermal infrared. We use absorption characteristics now of the CO2 band for a temperature profile retrieval. We have multiple water vapor absorption features, and like I said, a high sensitivity to clouds and aerosols. Here's the microwave absorption spectra again. In contrast, the AERI spectrum here, so very fine structures of mainly water vapor absorption, which we see in the infrared. We have a very large number of channels, around 2,000 channels. And we have red lines and black lines of the spectrum here, so we see what warm and humid case does to the measurements in contrast to cold and dry cases. So this is the forward problem I was talking about. If we have the atmospheric state, X, we can have a forward model that will give us the measurements, so that will derive this spectrum from the measurements. But the idea is, of course, to solve for X, and this is an ill-posed problem. So there are many atmospheric states that will give rise to the same measurement. But for this AERI, the solution is more distinct. So we can actually derive the profiles of water vapor and temperature much more accurate with this AERI system than with the microwave radiometer. So we see here the radiosonde in black, winter case, the summer case here, temperature, humidity, and the microwave radiometer smooths through this inversion and doesn't capture this minimum of humidity here in winter. But the AERI, on the other hand, can very well follow the basic structures of the radiosonde profile. But the AERI is also very sensitive to clouds, as I said. So if we have only very thin liquid water path of about 7 grams per square meter, this already gives us a very large offset of our spectrum with respect to the clear dry case. The offset is basically due to the optical depth of the cloud, and the slope is also due to the size of the cloud. So for very thin clouds, we can say something about the optical depth and about the effective radius, which is leading to this emission. So not only about the water content, but also about the size of the cloud droplets. But this signal was saturated at liquid water path signals around 60 grams per square meter. So we really need this microwave radiometer if thicker clouds appear. Another instrument is a ceilometer. This gives us backscattered radiation on aerosol layers, so we can say something about the mixing layer height, and we can determine cloud base with a ceilometer. So this is based on the LiDAR principle. So it sends out laser pulses and measures the backscattered light. We have a temporal resolution of about 15 seconds and a vertical resolution of 30 meters. Following the detection of the significant aerosol layer, so the top of the aerosol layer can lead to a retrieval for the height of the atmospheric boundary layer, which you can very nicely see at this view graph here. We see the backscatter. A low backscatter is in white, high backscatter is in red. We see the developing boundary layer in the course of a nice convectively driven day. So we see after sunrise how the boundary layer, so the aerosol particles start to be well mixed, start to rise. So we see how the mixing layer height rises, and at a certain point, a cloud base starts to exist around 2,000 meters. So this is very nice for viewing the development of the boundary layer. Total sky imager is another instrument that we have. It's very valuable because we have a visual addition to many other remote sensors, so we can have an eye-to-eye comparison. We can look at the hemispheric cloud structure and the variability and impacts on radiation. So we have hemispheric cloud observations. We have a camera that looks from above on a spherical mirror above here. The sun is blocked by a black tape, which is right here. So every second we get an image, and not only a visible image, but we have the RGB values, which we can use to also classify the observed clouds into the clear sky, thin, and opaque. Typical way pictures you can see here. So these are the movies we can then create of the boundary layer clouds passing through over the course of the day. Here the clouds as we see them in the visible, and the optical thickness of the cloud due to these RGB thresholds. Further instrument is the Doppler wind LiDAR. So what we can do with this is to gain information on the vertical wind profile. So we get the strength and the direction of the wind vector, so we can say something about the shear. But we can mainly say something about so we can get this vertical wind profile information from the measurements of the Doppler velocity along the line of sight. Does anybody know what a Doppler wind LiDAR is sensitive to? So what is the particulate giving the backscattering and the Doppler information actually? It's the aerosol, exactly. So this means that, of course, we can only get information in the regions where there is aerosol. So we can very nicely resolve the development of the well-mixed boundary layer and the turbulent processes also, which lead to clouds. So it's based on the LiDAR principle, sends out laser pulses, measures the backscattered light, delivers profiles again of the backscatter coefficient, but additionally to the accelerometer, measures the Doppler effect on small particles. So we get a long-sight Doppler velocity, and from certain scanning configurations, it allows us to derive the wind vector as a function of height. And this is done by so-called Doppler beam swinging. So if we have only an observation in one direction, we only get the Doppler velocity of the particles to or from my sensor. But if we use different viewing angles, swing back and forth, we can use trigonometrical functions to derive actually the vertical profile of the wind vector. Every 5 minutes we do this with a vertical resolution of 30 meters, and a maximum height is determined by the existing cloud, which we cannot penetrate, or the end of the aerosol layer. And so we get typical profiles. Here you can see the wind vectors. So the backscatter is shown here in color, and the wind vector are the white arrows, where you see that we have a northward component of the wind vector during the night, very slow, slight winds, and then during the day we get a turbulent mixing, so the wind vector comes from different directions but is stronger, as you see in the length of the arrows. If we look vertically, we can get information on the vertical wind with 1 second temporal resolution. So the boundary layer height detection here can be carried out by a second way, meaning through the detection of the vertical wind velocity variance. So where is there a very high variance of the vertical wind? This shows us where there's turbulence, and this shows us where convection is ongoing, and this shows us then where the atmosphere is well mixed. So we can see here over the course of the day how the vertical wind velocity rises as the boundary layer develops, and we can interpret this as the height of the mixing layer. Okay, due to time, I'm going to jump over this part, but this is a link to the current data at Jülich. So all of the instruments I've been showing up to now are basically available online. So you can look every couple of hours at the updates of the measurements we are carrying out, but there are also quick looks archives going back to 2011. So now the idea is to bring together the measurements in a synopsis. So the idea is getting enhanced information by bringing together the different sensors. Different sensors mean different spectral regions with different informations from these spectral regions. They also mean can mean combining active and passive remote sensors, for example. Remember that the cloud radar identifies very nicely where the cloud is, but deriving quantities or accurate quantities of water content from the backscatter itself is very difficult. But if we use passive measurements from a microwave radiometer, for example, as a constraint, we can get more information or better information on the profile, for example, of the water content throughout the atmosphere. So often you have many measurements of different instruments looking at the same sky, but it's not clear from one instrument alone actually what we are seeing. So where would you say if we have an infrared thermometer, an infrared pyrometer, so it's a broadband infrared sensor which is very sensitive to clouds, looking vertically, and we also have ceilometer and microwave radiometer measurements, which I'm not showing yet, but alone from this time series, where would you say are the clouds? Where's the clear sky? Any idea? We have a very high sensitivity towards clouds, so what happens with the temperature if a cloud passes over the site? So here's a very optically thick cloud, here are broken clouds. And this is the clear sky part, where we have low emission from the clear sky, from the water vapor mainly. But the clouds give us a very high emission signal. So here we have broken clouds. So we have a morning altostratus sitting somewhere around 3 kilometers, giving us a liquid water path, very continuous measurement. And then we have these broken boundary layer clouds, convectively driven in the afternoon, where we see clear sky passages in between, and these clear sky passages then corresponding to the minima in the liquid water path. And we even see some water vapor variability, which is also due to the convective clouds. Sometimes it's interesting to compare what different types of instruments tell me about the boundary layer height, the mixing layer height, for example. So here we have 3 different lines. We have black, gray, and so the black diamonds. We have the gray diamonds, gray triangles, and the ISO lines. All of them try to give us information on the mixing layer height. So the gray triangles are purely from the ceilometer. Remember, the ceilometer tells us nothing about the Doppler velocity, so I don't have any vertical velocity variance information. So this is purely based on backscattering thresholds from the aerosol layer. The black diamonds are then these Doppler LiDAR measurements, which only take into account the vertical velocity variance. And the ISO lines show the bulk gradient from a microwave radiometer temperature profile. So this is basically the difference of the potential temperature in a certain height and the difference of the potential temperature at the surface. So when this difference is 0 of a rising parcel, we have reached the level of 0 buoyancy, which could also be interpreted as the top of the boundary layer. But we see large differences. We see a difference between the ceilometer and the Doppler LiDAR here at the very beginning. Ceilometer sees an aerosol layer, but there is no classical mixing layer height. This is coupled to the residual layer of the night. So this may be misleading to interpret, or this is surely misleading to interpret these gray triangles as a mixing layer height. So this is where the Doppler LiDAR gives us much more reliable information. And also through the day there are aerosol variations which lead to very strong variations in the height of the boundary layer from the ceilometer alone. The black diamonds from the Doppler LiDAR seem to give a much more reliable information here. And this level of 0 buoyancy, well, this is probably not due to overshooting. of the convective elements, it's probably due to the low resolution of the microwave radiometer, because the microwave radiometer is very powerful in the lowest kilometer for retrieving the temperature profile, but as soon as we get higher, the vertical resolution decreases. So this could be an instrumental effect. So, but these are the differences we have to deal with, and we have to look at different instruments if we combine, if we are interested in one quantity. So we cannot take one measurement for one instrument for granted. We can also combine the clouds observations from TSI, for example, and the microwave radiometer. If we have the TSI image here on the right, the geometry allows us to make a coordinate transformation. So from the pixels we observe here, we can identify which pixels in the TSI correspond to an observation angle, for example, of 30 degrees elevation. And then we can, as a function of time and azimuth, then show these circles as line plots. And when we see then the development of the cloud as a function of time and direction. And we can do the same thing for the microwave radiometer, which is doing elevation scans at 30 degrees every couple of minutes. And then we see interesting signatures. So we see similar optically thick clouds here, and we see liquid water path values shown here, which correspond to the dark parts of the cloud. So we can see visible and microwave signatures in the same plot. And actually, what we are seeing here is the plume of a power plant from the coal mining, which is visible very frequently in our measurements. So this gives us the idea that we can combine the visible and the microwave measurements. For example, we can overlay also the liquid water path isolines over these measurements from the TSI. And we see where the isolines are very dense, we have very high liquid water value paths. And we see that in some cases we have cloud free, so we don't have any concentration of isolines here. But we see also the concentration of isolines, which shows us the liquid water path from the microwave radiometer, varies from cloud to cloud. And we can use this, for example, to identify ice clouds or discriminate ice clouds from liquid water clouds, for example. A further further method of combining instruments is a target categorization, which we can derive using radar, LiDAR, and microwave radiometer together. So before we can apply any retrievals where we need to apply, for example, a forward model, we need to know what we are dealing with. We need to know, is it an ice cloud? Is it a precipitating cloud? Is it a drizzle cloud? Is it a pure liquid water cloud? And combining these three instruments allows us to derive this categorization. We see here again a time-height cross-section. But this time-height cross-section is now colored in different regimes. And these three instruments can give us thresholds where we can say, well, this part here is mainly cloud droplets only. So we have no precipitating clouds. The red parts are then the drizzling or the rainy parts, where we have, for example, high fall velocities from the cloud radar. And the yellow parts are the ice parts of the cloud. So we can use this to discriminate phase and cloud type. And this is really necessary to do the forward model transfer leading to the measurements that I want to simulate. Okay. So I'm going to skip over the quantitative synopsis part. So what can we use these measurements for that I've been showing? One part is to use them for the evaluation of numerical weather prediction models. So what we see here is a time-height section of temperature. These are a couple of days model output, which have been summarized in in this mean diurnal cycle. And we see the corresponding measurements from a microwave radiometer. And we can use these diurnal cycles from the model and from the measurement system to compare these model output to the measurements. And we see, for example, that the model underestimates the cooling in the stable boundary layer in the early morning hours. We see a strong cooling, radiative cooling effect, which the Cosmo cannot capture in the mean. And in the late afternoon, models cool too quickly, basically. We have a longer warming of the boundary layer in the HAT-PRO measurements, in the microwave radiometer measurements. And this, for example, could be due to clouds, or it could be due to the wrong capturing of radiation interaction. Now, imagine we had only conventional radiosondes, even 3 times a day, which is more than at a normal station, which are only at 0 and 12. But if we had these 3 radiosondes we had here, we could not capture these conventional diurnal cycles with using only these measurements at these distinct times. So this is the exclamation mark behind the measurements of a microwave radiometer, for example. So what we plan at JOYCE is to use JOYCE as an LES model testbed. So an LES model is a large eddy simulation model which can resolve parts of the turbulence spectrum explicitly. Parts of the turbulence spectrum are still parameterized, but parts of the turbulence spectrum are explicitly resolved. And the idea is to continuously run such a model over the JOYCE region together with our colleague Roel Neggers at the University of Cologne. So we intend to have a domain size of 25 by 25 kilometers, reaching to 8 kilometers with a very high resolution, and to continuously force this model with the thermodynamic JOYCE observation data. And to include into this LES model cloud microphysical schemes that may even resolve the drop size spectrum in detail. And then the idea is to follow or get on to certain questions. So do the statistics of these LES models that we have in the model, LES clouds, agree with the scanning measurements we have at JOYCE? Or what parameterizations in the model do we have to adjust so that model and measurement will coincide? And then, of course, how crucial is the role of the surface forcing on the clouds and vice versa? Because we can include different schemes, surface schemes, in the LES model. And we can see how important the surface is under certain forcing conditions for the development of clouds. So instead of just observing, we can also look into the model and see what processes we can capture and what not, and turn on and turn off certain processes to see when the observations are met. And I would like to show you this movie at the end to see what these LES models are capable of and to see what we are going to be comparing our observations with at the end. So this is an LES model run over Jülich already, and we see a vertical column over Jülich, and we see for a convective day that clouds will be appearing at a certain height in a certain structure with a certain overlap. And of course we also have the information on how much water is in the cloud and at what height, so how long a cloud exists and so forth. So these are the clouds we want to be comparing our measurements with. Okay, so at the end, I will come to my summary. I hope I could show you that JOYCE is a super site that operates continuously since 2012. We have the possibility to characterize the thermodynamic state and the dynamic state of the cloudy boundary layer by means of novel ground-based instrumentation. We need sensor synergy for a more complete picture, for maximizing the information content in our retrievals. And currently, I didn't show the clear sky information content study, but we are trying to figure out what instruments do we need to combine in order to get a maximum information content on the cloud retrieval? So various ground-based remote senders, I hope I could show, allow to monitor in detail physical processes in the boundary layer. And we are aiming at a better understanding of the cloud processes through the use of LES models. And one goal in the future is to especially improve the representation of clouds in numerical weather prediction and climate models, and at the end maybe be able to use our observations to adapt microphysical parameterizations. Yeah. And of course we are also working with groups that are not only dealing with clouds and microphysics, but especially also on the aerosol influence and the plant and surface influence on the interaction of clouds and the other part of the climate system. That's it for me, and thank you for your attention.